Hi, I'm Bruce Clark, General Manager of a.i.tek. For over 50 years, a.i.tek has been providing reliable, predictable, cost-effective monitoring and control devices for some of the most demanding speed sensing applications on planet Earth and off. a.i.tek started life as Airpacks, a small industrial division of Fortune 100 companies. We are now privately owned, boasting all of the quality systems of those larger companies and the personal service and entrepreneurial spirit found in the best small companies. We are AS9100 ISO 9001 certified, and our sensors are made in the USA. I hope you will find the following training helpful in gaining insight into a.i.tek, the company, its products, and numerous applications we serve. Thanks for your interest in a.i.tek. Welcome to Variable Reluctance Speed Sensor Training, another installment in our profile training series. Start out by giving you an idea really what is a speed sensor, and it's the bridge. It bridges the gap between the mechanical and the electrical world. They produce a frequency that's proportional to the speed of the target. There's not a whole lot of magic to it, but the idea is that's the basic language that then gets communicated to a control device to help it understand what speed and or maybe direction that the target is moving in. a.i.tek offers two basic sensor technologies that really are the foundation of all of the speed sensing that we use. First is variable reluctance, also known as a passive speed sensor. You might hear other names for it, but those are really the two most popular. Transducer, I think, has been used occasionally. Anyway, so the variable reluctance passive speed sensor is essentially a generator, and it's a two-wire device. So that can be very popular, especially if wiring considerations. 2 wires are cheaper than 3. And if weight is an issue, let's say on an aircraft or whatever, the 2-wire setup works. It's also the setup, again, passive speed sensor has been around a very, very long time, and so chances are if you have an installation already, there's 2-wire cabling already available. The output of the variable reluctance speed sensor is a sinusoidal waveform, same wave shape really that comes out of the wall that your normal 120 volt power comes out. And so there's peaks and there's a zero crossing. Okay, Hall effect is the other technology that we will be talking about in another series. We'll go over it in a little more depth, but just to kind of compare the two right now, the active speed sensor, or Hall effect as we make them, is a 3-wire device. It requires power and a ground, and there's a signal output, and the output wave shape is a square wave. Again, we'll go into that in more detail when we do the active speed sensor training module. So again, as we discussed, passive sensors may be known. So when you're out there, they may be known as variable reluctance speed sensors. And really, that kind of leads to the first bullet point, where magnetic resistance is known as reluctance. And really, it's impeding the ability of the magnetic field density to do its job. And the reluctance really is that we use in this particular application is air gap. So there's a little drawing down here, and it shows a section of a target with 3 teeth. You have the tooth and the valley, and then you have 2 sensors. Really what it is, it's showing the internals of the sensors, and there's a pole piece, there's a coil, there's a magnet on the back. These lines here are the magnetic lines of flux, and they go around the outside of the, from one pole to the other. And the idea is when a tooth is positioned in front of a sensor, and the air gap now is smaller, the reluctance is lower, and when that target moves, you have a valley. That reluctance now increases. So you go from a buildup of magnetic flux to a reduction in magnetic flux. That collapse of the field induces a voltage in the coil, and that becomes the output of the variable reluctance sensor. Repeating combinations of that tooth valley, those combinations produce that sinusoidal electrical output signal. One thing to remember about passive speed sensors, as the rate of change of the magnetic field increases, so does the amplitude. So the faster it goes, the higher the output will be. So there's a little diagram here showing this. These peaks are known as, that's the amplitude. And so those peaks grow further and further away from the 0 point. It just gets higher and higher. As the speed decreases, conversely, then those amplitude peaks will decrease. And that can cause some issues when you're kind of trying to engineer an application. So you have to be careful with that. The other thing is air gap. As the air gap increases, the output decreases. As the air gap decreases, amplitude increases. So we'll talk a little bit more about that a little bit more later. Okay, so each sensor has a characteristic output curve. And when you look at this particular graph, unfortunately, it kind of looks like it's an exponential output. So you get speed on the bottom and you've got output going on the vertical axis of the graph. And it looks like it's rising exponentially. Unfortunately, the way the graphs were made back in the day, it's a semi-log graph, so that the combination of a linear scale and a logarithmic scale here creates this exponential rise looking waveform. What it is, it's quite linear. So as the speed increases proportionally, the output increases proportionally. It's quite linear. And so with that characteristic in mind, one can use those curves to then, you can know there's guarantee points that we provide by these marks on the waveforms. Each waveform has a characteristic air gap that it was set. So the higher the output here, the gap was the smallest. It's 5/1000ths of an inch, then it goes to 30 and 60. And all of our speed sensors carry that, especially in our catalog. And the idea is, you can take a look at this and you can actually then predict, well, if I go higher than this particular speed, what's my output going to be? And if I go lower, what's my output going to be? All right? Don't want to get too technical here, but I think it's a good idea to kind of just go over the output waveform a little bit and give you a slightly better understanding. So on an output waveform, this is the ideal looking waveform, right? You see this nice sinusoidal waveform, and you can clearly identify logic levels that you might want to switch off of, a logic high level and a logic low level and zero crossing and everything. But in reality, what you're going to see is this. So the real world imparts noise on that signal. And so when we were talking before about the slower you go and the wider the air gap you go, the lower the output. If you can imagine, if you have 1 volt of noise and you have a 0.5 volt peak-to-peak signal, the noise is greater than the signal, and it makes any device that's trying to read this, it's a very, very difficult time for that device to really understand. You can see if between these two lines, there's the truth in there somewhere, but it can become more and more difficult. This one isn't too bad, but again, as you can see, if that amplitude drops too much, that noise is just going to become overwhelming to the signal. So the logic thresholds that we try to maintain, they define a viable sensor of pulse, and that's how our tachometers think about it too. They just want to see, okay, well, did you make this threshold and did you make that threshold? And if you did, then I can judge that as a good pulse. Our tachometers do it, our competitors' tachometers do it, and all other kinds of reading devices. They're all looking for these thresholds. They may all also be using a zero crossing, but again, if you got a lot of noise on there, where did that zero crossing really occur? All right? The difference between this logic high level and this logic low level, that's the noise margin. And that, the more distance you can put between the two, the more noise you can have on the signal, and the better noise rejection you can have. So again, the high level minus the low level, the difference there is the noise margin. And again, when you're looking at applications, and you're wondering why things aren't working, this is one place to really look initially to see what the quality of that signal is. When you're looking at variable reluctance sensors, some of the features, they sense gears or any ferromagnetic discontinuity. Basically, gears, if you look at power transmission gears, they have teeth and valleys. That is the ultimate way that's the best type of target you can have, but you don't have to do that. We use gears because it's an industry standard. Everyone can recognize if you have a 20 diametral pitch of gear or whatever, those teeth and valley, the dimensions of that, the pressure angles and everything, it's all defined, and so when we test, we know how it's going to work if you're using that. But again, that's not an absolute necessity. People cut slots in targets, they use keyways, they use the keys themselves, they drill holes, they do all kinds of stuff. The sensors are really quite applicable to a lot of different types of targets, and so don't worry that it's not a perfect target. It's just, we like to have a standard that we work off, and it just, if you have a particular target that is different, what we can do is we like to get involved in the application engineering side of this as soon as possible. So if you have a very strange target, it's best so that we can take a look at it and help you engineer and make sure that where you're headed is correct. Another feature, there are no moving parts or contacts to this device, or there shouldn't be anyway. And so, there's not really much to wear out. And that's one of the reasons why the variable reluctance speed sensors, really, they've had such a good history, and they were well recognized in the industry. They are wired with 2 wires. There's no power required. They're great in harsh environments. Especially the ones with a blind end where the stainless steel housing covers in the front. There's not much to go wrong, and so they do well under pressure. They do well, when they're exposed to oils and other chemicals and that type of thing. They're great in high temperature. We can select materials, and right now we're looking at 750 degrees F, 400 degrees C. Max. That was really kind of an old standard. I added the bullet item down below where we're currently working on designs that will exceed 1,000 degrees Fahrenheit. And again, it's the same basic coil design, but it's the material selection and how you put them together that allows them to survive in those temperatures. Some of the benefits, they install very easily. Most of what you'll see they're either threaded housings, and so 2 jam nuts and a bracket, threaded casting, anything like that, they install very easily. Some of them are built onto flanges, especially the custom ones. And so, 2 bolts, and it sets the air gap and everything. It's very, very simple. There's no alignment when you're threading it in. You don't have to worry about rotationally. All you got to do is you got to get the air gap right. That's all. Very, very reliable, very mature technology. And these things have been around for a very, very long time. They carry with it, a high degree of confidence with a lot of people. So this is definitely a good way to go if that is one of your key issues. And low cost. They're not cheap per se, but when you look at it in comparison to an active sensor, they are low cost. What drives the cost is all the customization, the special targets, the special housings, the high temperature materials. Those things tend to drive the cost up, but the basic technology tends to be a lower cost. So some of the limitations, things you got to worry about, we talked about this with the air gap and speed. So here we're talking about poor low speed performance. Anything below about 100 RPM or 15 inches per second really is a practical threshold. That below that, it's not that the sensor won't work, but like I showed you with the output waveform and the noise on it, if you go too low, it becomes a real problem, and so it requires a higher level of engineering. Maybe we got to make sure the noise is not in there. Maybe we need to make sure that maybe we're running a smaller air gap or more turns on the coil. Maybe it gets to be custom. But anyway, when you get below that threshold, more engineering. Above that threshold, a lot of, I'd say 90% of our applications really don't require any application engineering at all. It's just you put them in front. As long as the pole piece is pointing towards the target, it's going to work. And then, related to that first bullet item is a second, where the output amplitude is dependent on the speed in the air gap. So if you've got thresholds, really when you're designing the application, then what you have to do, since if you're looking at a slower speed, let's say, what you need to do is design the application so it works at the lowest speed, and then you don't worry about the high. You calculate all your calculations, all your design work is centered around that lower number. Some family photos of the sensor products. These are more of our military and aerospace. You can see on the top the The long one, this one is a long reach. This is actually fairly complex, and that low cost thing we were talking about, this is not a low cost VR sensor. There's a small coil in the front, wires come to the back, there's a transformer in the back. That transformer steps up the voltage from that small sensing coil in the front, and then it's output through a mil standard connector in the back. And you can see, this one has some threads on it. There are a lot of mounting brackets so that, from this surface to the tip, that defines the air gap. So for that particular customer, they just want to be able to bolt and go. It's very, very easily replaced. The right angle connector. So it's those kinds of things that make them unique and customized. Another family photo, a lot of VR sensors in here, some very, very strange applications. But just to show you the range that we cover, different housing types, cables, wires, connectors, materials. Those are the things that separate and make the VR sensor, of greater value than just a standard off-the-shelf type sensor. More photos. Here, this is give you a little sense of scale. The smallest sensor we make is based on a 1032 screw, just about the size of a dime. And then up here we're talking about some of these large, trucks, fire engines, buses, that kind of thing. This device is what we call our side look sensor. And instead of the pole piece, this one has a pole piece right in the center. There's no pole piece here. The pole piece actually wraps around here. It's called the side look sensor. And it plugs into a tail shaft on a transmission and replaces a speedometer cable. So rather than having a cable that can go bad and break and everything like that, then here you've got this signal coming out on wires, and it can go to an electronic control. We have a number of hazardous location, highly pedigreed sensors that again allow you to go into hazardous locations. And there are different protection strategies that it's worth going over a little bit. The first one, again, this is the way we utilize. There may be some slight differences you might see from other manufacturers, whatever. But the first protection strategy is it's explosion proof, and that's based on North American standards. And typically you'll see it as a UL or CSA certification. And again, they're based on North American standards. The whole premise here is the device is designed to contain an explosion or ignition in the environment that it's in. So it says it can have an explosion, but just don't let that ignition propagate out to then into the rest of the area, which is probably filled with a hazardous or flammable gas. Okay. Now, one important note: the device can fail in its normal intended function, and probably the safest sensor in the world is a dead sensor, because then it's not producing any energy and it can't cause a problem. Intrinsic safety, that's the next protection strategy. Intrinsic safety or non-sparking, and you'll see them as FM, a.tek, or ICEX. And what this one says is that the device will not produce enough energy to become a source of ignition. The first one says, yeah, we make a lot of energy, but we're going to contain it. The second one says we're not going to make enough energy to cause a problem. All right, again, the device can fail under its normal intended operation. So layered onto that, what we've done is we've gone out and we've gotten SIL, safety integrity level. And the safety integrity level, we have a third party that evaluated our sensors and says, under normal intended function, your device is highly unlikely to fail. And so we're not going to do any harm with our protection strategies, and we're always going to be there for you. So the SIL and then your selected protection strategies, the two together, that's a powerful pedigree that allows us to get into a number of hazardous locations. And here it's really the same information. It's grouped a little bit differently. For the UL CSA, we do, if you're familiar with the North American setup, they do classes and divisions and gas groups and that kind of thing. So our sensors are listed for class 1, which is what it describes, flammable gases. Division 1 says that those gases are under normal operation, and then the gas groups A, B, C, and D define the hazards, the specific gases, and then also Class 2, which is that describes ignitable fibers and powders and that kind of thing. When you move into the intrinsic safety, the IEC-EX, the a.tek, and the FM. The FM tends to stay with the North American standards, but when you get into the a.tek used European norms. IEC-EX actually is still using essentially the same standards, but they vary slightly. What we do is we've got different zones. So the Zone 1 and the Zone 2. Zone 1 is a method of protection that gives us intrinsic safety. It needs to be used with a barrier. The Zone 2 is more of the non-sparking, non-incentive type protection that allows the sensor to be used without a barrier, and it's a lower degree of protection than the Zone 1. And the IEC-EX is a Zone 1. It's the same zones and categories and groups as used in the a.tek, and the Zone 1, of course, still uses a barrier. It's necessary for making sure that you're compliant to the standard. Okay, that's the end of variable reluctance speed sensors, and please take a look at the other training modules that we have in the series: company introduction, the active speed sensors, and tachometers and accessories. Thank you.